Hello everyone, I'm Chao from Guangzhou University, and today I'll be presenting our collaborative work on CORES Convolutional Response Score for out-of-distribution detection. Our study addresses a crucial challenge in deep learning, particularly in the context of neural networks and their behavior when encountering unknown data. Typically, neural networks follow the closed-word assumption, meaning they are trained within a closed environment using data we refer to as in-distribution data. If during the inference stage, the neural network encounters data that is also in distribution, it can achieve excellent performance. However, when deployed in the real world, it will encounter unseen and unknown data, known as out-of-distribution data, which can lead to various safety issues. Given a DNN classifier trained on a specific training set, when inputting unknown OD samples, we expected the classifier to output uniform low-confidence predictions, but it is likely to output overconfident predictions. We call this phenomenon the problem of overconfidence in OOD. The OOD overconfidence problem poses safety risks for real open-world applications, such as robots and autonomous driving. Even worse, studies have shown that the OOD overconfidence problem in neural networks is unavoidable. Currently, there are two main solutions to the OOD overconfidence problem. The first approach targets the root cause of the OOD problem, the lack of explicit OOD knowledge during neural network training. This can be addressed by introducing real OOD auxiliary datasets during training, synthesizing OOD samples close to the edge of the ID distribution using transform gun, or sample outliers directly from the future space to create virtual OOD futures. By suppressing the network predictions for these samples, the OOD overconfidence issue can be mitigated. However, these methods often require a large number of OOD samples and can inevitably affect the original classifier performance. The second approach treats ID and OOD detection as binary classification tasks. The simplest method involves setting a threshold on the output softmax confidence. Other techniques, including using temperature scaling and forward perturbation to make confidence scores more distinguishable, measuring the Mahalanobis distance of samples from the ID class centers in the future space, and utilizing energy score. Work is based on the observation that convolutional kernels generally exhibit more pronounced response to ID data compared to OD data, as they are trained on ID patterns. As shown in the figure, we visualized the responses of the last convolutional layer in ReStat 18 for two OD datasets. The axis represents the channel indexes, and the y-axis shows the response magnitude. ID data clearly elicits more pronounced response than OD data in both positive and negative reduction. Based on the above finding, the first problem we need to address is what metric can be used to capture this difference. We developed an OD score based on the convolutional response, utilizing two main directions. First, kernels exhibit stronger response to ID data measured by the RM metric for response magnitude. Second, kernels exhibit more pronounced response to ID data assessed by the RF metric for the frequency of significant response. Ultimately, the OD score is calculated from the product of these four metrics. The designed score effectively captures differences for OD detection, but do all kernels respond as expected? Does sample random kernel exist? In fact, each layer in a DNN has many convolutional kernels, but only